3.
Hi guys, so today we're going to talk about using variables as a problem-solving strategy, and my name is Camry Sievers. To start out the day, we're going to play a true or false game. So number 1 is 5 plus 5 equals 20.
False.
True or false? Correct. Number 2 is 6 plus 7 equals 13.
True.
Good job. Number 3 is 2 minus 1 equals 1.
True.
The equations we did on the last slide were true and false, but today we will be working with equations that are neither true or false, but are open and have a missing number to be solved. Also, many times not all the number values are given and there are missing add-ins. For example, how would you compare blank plus 5 equals 12 to the problems we were just doing? The answer is given and one of the number values is not. So what is a variable in a variable expression? A variable is a value that is unknown and is represented by a letter or a symbol. A variable expression is an expression that contains at least one variable. Variable expressions can be evaluated. This means we can substitute or plug in constant values for the variables and determine the numeric value of the entire expression. Now we are going to do some problems together. Number 1, evaluate for x equals 5, x plus 3x. The solution would be to substitute the values for the variable. X plus 3 becomes 5 plus 3 times 5. Now complete the numerical expression using order of operations. 5 plus 3 times 5 would become 5 plus 15, which would be 5 plus 15 equals 20. Number 2 is, which of the ordered pairs is a solution of the following equation? Negative 3x minus y equals 6. Would it be negative 4 and 4 or negative 3 and 3? Solution. Remember, the first number in the ordered pair is the x-coordinate and the second is the y-coordinate. So let's plug in negative 4 for x and 4 for y. Negative 3 times negative 4 minus 4 equals 6. Now we solve using order of operations. 12 minus 4 equals 6. That does not seem right. So we try the second ordered pair, which would be negative 3 times negative 3 minus 3 equals 6, which would come out to be 9 minus 3 equals 6, which is correct. Now you guys are going to do a problem on y'all's own. How would you solve this problem using what you've learned today? Jackson is thinking of an integer which, if you triple it and subtract 13, ends with the result of 2. What number is Jackson thinking of? Use a variable. The solution would be, let m be Jackson's number. To triple m and subtract 13 means to compute 3m minus 13. Thus, 3m minus 13 equals 2. So m equals 5 because 3 times 5 equals 13 or 15, which equals 2. So m would equal 5. Conclusion. Now you have learned a little bit about variables and how to solve variable expressions today. I hope you guys had fun learning. Now Claudia is going to talk to you guys about working backwards and eliminating possibilities.
Growing up, did you ever get in trouble for looking backwards? Maybe your teacher told you to face forward while you were talking to a friend, or your parents got on to you for looking behind you rather than watching where you were going. Today, I'm going to have you look backwards in math. My name is Claudia Kemp, and today I will be discussing 2 different problem-solving strategies to help build your creativity and broaden your mathematical skills. The first strategy is working backwards. Working backwards is used when a problem gives a series of steps, each affecting the one following, and an answer without a beginning or a starting point. In order to work backwards, one must undo the mathematical equation that has just been done. For example, if the answer was found through addition, subtraction would be performed to undo it. Once each step has been undone, the end result should be the beginning of the original problem. In order to check your work, simply plug your answer into the beginning of the problem and work as normal. Easy. The second strategy is called eliminating possibilities. Eliminating possibilities is used for problems where there is a set amount of information given, but the goal is missing. It requires the individual or student to determine what information is useful, what is unnecessary, and what is a possibility. Data tables are very useful in this strategy for sorting through the information. Say there are 3 men and each one leaves the house on accident with a different one's scarf or hat. You would use a data table to organize the information that you currently have and to find where the gaps are to determine what needs to fill those gaps and what would not fill those gaps. Students must organize the information given and weed out that which is not a possibility and those that are less possible. A very popular example of this strategy is the game Guess Who, where you use questions to determine possibilities and not possibilities. For example, if you were to ask, is the person redheaded? If the person was redheaded, then you would be able to knock down all the people that weren't redheaded. And if they're not redheaded, then you knock down everyone that is a redhead, thus eliminating possibilities. Very easy strategy. I hope you learned something today about creative problem-solving strategies and that it's helped you broaden your mathematical skills and will help you to further your mathematical pursuits. Up next, we have Alexis Johnson talking about the pigeonhole principle.
Thank you, Claudia and Camry, for reviewing a few of the problem-solving strategies in Module 1. Today, I'm going to introduce you to the pigeonhole principle. My name is Alexis Johnson. Have you ever wondered what pigeons and math even have to do with each other? Well, today I'm going to clear that up with you. The pigeonhole principle states that if n items are put into containers with n being greater than m, then at least one container must contain more than one item. This is a very simple concept. It's basically common sense. I have 2 photos down here that are very similar problems that are pretty easy. So there's 10 pigeons right here at the left, and there's one that is still left that needs to go into a pigeonhole. Well, there's only 9 pigeonholes. So no matter what, there's always going to be more than one pigeon in one of these pigeonholes. There's no way around it, no matter how you organize them in their pigeonholes. And the one right here is there's 4 pigeons, and you can evenly distribute 3 of the pigeons, but the 4th one would have to go into a pigeonhole with another. In the pigeonhole principle, the pigeons are actually the objects. These are just metaphorical words that they're using. The pigeonholes are categories or containers that the objects are being placed into. Some real-life situations that the pigeonhole principle could be used for. For example, my example 1 is you can use the pigeonhole principle in infinite ways. An example is if you have 10 black socks and 10 white socks, and you're picking socks randomly, you'll only need to pick 3 to find a matching pair. The reason for this is because there's 2 colors. So if you pick one up that's black and you pick one up that's white, no matter what, the 3rd sock you pick up will be white or black, so you'll have a pair. Or if you pick up the first 2 are black, you're already done. So either way, if you pick 3, you're no matter what, it will In example 2, imagine if you pick 5 cards from a standard deck of 52 cards. Then at least 2 will be of the same suit. Each of the 5 cards can belong to one of 4 suits. This is true. There's only 4 suits. If you pick 5 cards, then you're picking over 4 suits, so you'll have a pair after that. The importance of this principle. This doesn't sound like the kind of stuff that sets the world on fire, but it can be a powerful way to look at different mathematical problems. Sometimes we want a distinct answer for every possibility, input a wide range of data, and get a wide range of output. The pigeonhole principle shows that this is not always possible. In many situations, no matter how extensive the number of outputs, there is going to be a collision in which distinct input data get stuffed into the same pigeonhole. What would happen if you had 10 pigeonholes and 11 pigeons? How would this problem be solved? Well, according to the pigeonhole principle, since there are more pigeons than pigeonholes in this problem, then there will be at least one pigeonhole with more than one pigeon in it. To solve this, you could simply draw a picture or representation and figure out the possibilities of pigeons and pigeonholes. To the right, there's a photo that's a very similar situation of that type of problem. In conclusion, the pigeonhole principle is a very simple yet a very useful strategy to use in problem solving. You use the pigeonhole principle if you have items to consider that can be placed in different categories, but you have more items than categories. Then at least 2 items must be put into the same category. The pigeonhole principle is quite trivial, but it is very powerful in mathematics. Thank you. So yes, the theory did form from actual pigeons and their pigeonholes, but it is much more than that. I hope you enjoyed learning about why pigeons are relatable to math. We as a group hope you find these problem-solving strategies beneficial to you in the classroom and in real-life situations that they may apply to.